Let's continue our look at the basic ingredients of science. There's reasoning. We have brains that distinguish us from all the other animals. Oh, I do think dolphins and orcas and elephants are smart, and perhaps they have reflection and self-consciousness and the awareness of death. But only humans have been able to figure out their place in the natural world and underlying laws of nature that govern our existence. And these brains have been in our heads in a modern form for about 40,000 years. Now, we've learned how to do something with those brains, and the rudiments of logic, of course, come from Aristotle. He put together the rules of deductive logic, and so we can see, because animals are not as smart as we are, how there can be failures of logic, as in these two examples. Deductive logic is the basis of science. It combines statements or premises to reach a conclusion. And the conclusion is valid only if the premises are justified and the logical construction is correct. Deduction preserves truth, but it doesn't always expand knowledge. An example of deductive logic is arithmetic or algebra. So mathematical systems use deductive logic, but you can also use words as well. In this example, we can imagine that we have observations that tell us that the Earth is larger than the Moon, and separate observations that say the Sun is larger than the Earth. These two statements can be completely reliably combined by deductive logic to say the Sun is larger than the Moon. So while this is true, you can see that it's a little sterile. It doesn't seem to add anything. It combines two statements that are clearly valid and true to another statement. But the building blocks of logic are obviously valuable. The entire edifice of mathematics and arithmetic are based on them. Meanwhile, there's a second form of logic called inductive logic. Inductive logic is a complement to deduction because it involves a generalization from a limited amount of data to a broad conclusion. Induction cannot yield certainty, but backed by sufficient data, it can give reliable conclusions. Induction expands knowledge, and so it is a basic tool of science. And here we see the example of Newton, of finding a theory of gravity that explains the orbits of a limited number of planets in the solar system and the Sun and the Moon, that's then generalized to a universal law of gravity to apply to planets as yet undiscovered, to apply to stars in the galaxy as yet unobserved, and in fact it does. So Newton's law of gravity is a fabulous example of the inductive method of science. So notice you get something, but not for nothing. You get the expansion of knowledge, so it's a basic tool of science, but the data that's the basis for your induction is always limited, and so theories are always subject to verification. And so another ingredient of science comes from this. It's uncertainty. Uncertainty is not a bug. It's a feature of science. It's always there. And our goal is just to understand it, to measure it, and to manage it. Astronomers use estimation, which is an order of magnitude calculation. It's not possible or even necessary in astronomy in particular to derive very accurate numbers. The objects under consideration are usually very faint and very far away, and our data is limited. So for many exploratory calculations in the subject of astronomy, a factor of 5 or 10 accuracy is good enough to tell you if you're in the ballpark. A factor of 2 accuracy is good even for some numbers in cosmology, the size, the breadth, the scope, the contents of the universe. And 10% accuracy is about the best we get for well-measured parameters in astronomy. Now we're approaching 1% for some numbers like the age of the universe. But astronomy is not a highly precise science. And the point is that when you're in the exploratory phase of any science, having an uncertain number or an estimate is not a problem. It's just part of the process of how you get to the better answer. And sometimes it's always good enough. Science is limited by uncertainty, by imprecision, by error. And these three words have very different meanings in science, and quite specific meanings. So there's conceptual uncertainty. It's the idea of making a false premise or confusing correlation with causation, something we'll talk more about in a minute, or inferring a pattern where none is present, jumping to conclusions if you like. There's large-scale or macroscopic uncertainty, which is the fact that there's no such thing as perfect data, Every data set is limited, and every instrument, microscope, telescope, atom smasher, has its limitations. And then there's microscopic uncertainty. This is uncertainty that's only been known to us in the last century, since we had a quantum theory of physics. Heisenberg's uncertainty principle sets a fundamental limit to the precision for measurement of the material world in various combinations of properties, like position and velocity, or energy and time. And it's important to note that this uncertainty is not a fault of the measuring apparatus. This, we believe, is built into nature. Let's look at how this quantum uncertainty plays.
It upset Einstein very much, you know. All that damned quantum jumping. It spoiled his idea of God, which I tell you frankly is the only idea of Einstein's I never understood. He believed in the same God as Newton, causality, nothing without a reason, but now one thing led to another until causality was dead. Quantum mechanics made everything, finally, random. A thing could be this way or that way. The mathematics deny certainty, they reveal only probability and chance. And Einstein couldn't believe in a God who threw dice. He should have come to me. I would have told him. Listen, Albert, he threw you. Look around. He never stopped.
Causality. This is another underlying principle of science. Just think about it for a minute. Scientists look for reasons for things to happen. Nothing happens for no reason. In a sense, we're looking at phenomena or effects, and we're trying to discern the underlying causes. For a moment, just think of how difficult it would be to make sense of the world if we did not believe in cause and effect. If we did believe somehow that things happen for no reason at all, that the universe is random and chaotic and unpredictable. That's not our experience. Well, not generally our experience. And in fact, science is built strongly on the idea of causality, of effects that have causes that even if we can't always see them directly or immediately, they do exist and we can eventually identify them. On the other hand, the universe doesn't work like a perfect machine or like clockwork, where everything is perfectly and completely predictable. We'll see this issue when we talk about Newton and gravity and the science as it moves forward in time. So determinism is an important idea from philosophy that also applies in science. If we could measure the properties of every particle, their motion, their temperature, their velocity, their position, then in principle calculate with sufficient accuracy, the universe would be like a big machine, like a clockwork universe where we could predict everything. And in such a perfectly predictable universe, what is the role of free will? It's a big philosophical question. And so the idea of determinism, which does exist at some level in science, or science would not be able to operate, becomes a profound area of discussion amongst scientists and philosophers. Correlation is based on observation of the natural world. Scientists will measure two properties of something and put data points on a graph, and maybe there's no correlation, nothing to see here. So they gather more data and more data. And as they gather more data, well, perhaps it's interesting. Perhaps it does look like X and Y, whatever they might be, are actually correlated, that the bigger X is, the bigger Y is. And then we might wonder, what is the reason for such a relationship? And so we gather more data, and that's how science progresses, of course, by gathering more data. And in this example, as we gather more data, the correlation persists, but it's no longer so simple. It looks like it's curving upwards, which would be a nonlinear correlation, the relationship getting steeper as X and Y get larger. And so this is the essence of science, to look for relationships between observed quantities and then understand the nature of the exact mathematical relationship and the physical cause behind it. But we can be fooled. Here is a fairly well-known correlation, I'd be surprised if you hadn't heard of it, between, on the world, the average temperature and the number of pirates, seen historically. So more pirates correlate with higher temperature. That's very interesting. Is there something about temperature that makes people turn into pirates? Well, no. There was a relationship with an underlying variable of time. Temperature increases with time, and the number of pirates increases with time, and that's the underlying correlation. This is just an apparent correlation, which might fool us into thinking there's a relationship between how hot it is and the likelihood of being a pirate. Let's look at the coin. The coin is a good example for some of the quantum issues we're going to be talking about later. A coin can only be heads or tails, and it could be neither or both in the quantum world. And so probability has to take a more complex form when we consider the natural world through quantum theory. So we've had to develop a more nuanced idea of probability, of outcome, of eventuality in the physical world in modern physics. Some events are individually unpredictable, but the statistical average is well determined. For instance, the roll of a single dice is unpredictable. Each outcome has a 1 in 6 probability of occurring. Yet on average, we know that at a large number of rolls, we will see 1/6 at a time a 6 come up, 1/6 at a time a 3, and so on. And that fraction gets closer and closer to 1/6 the more rolls of the dice we have. Similarly, with the radioactive atom seen on the right, it's impossible to predict when any single radioactive atom will undergo a decay. It's just impossible. But if we have a collection of these atoms in a sample of a radioactive material, then we know that on average, in a particular time called the half-life, 1/2 of these atoms will decay. A more common and mundane example might be a pan of popcorn. You can cook a pan of popcorn in a predictable way such that you know well when 1/2 of the kernels will have popped. But if you look at the pan as they're about to pop and try and predict which of the kernels is going to pop first or second or last, you can't do it. The individual kernels are unpredictable, but the collective is predictable. And a different pan of popcorn copped in the same way would produce the same time for 1/2 of the kernels to pop. So we can have individually unpredictable events where the statistical average is well determined, and that's a core feature of science. The average properties of the system become clear, and so we get the smooth histogram, the distribution of events, and for the radioactive atoms, we get the half-life curve. And that's the end of this topic.